Swayam Prabha. Digital India. Educated India.
Good morning. Let's continue our discussion on the development of finite element equations for solid mechanics. In particular, we are looking at the 2D, which have slightly simpler equations compared to 3D, but however, they exactly follow the same procedure. So these are the equations which we had in the last class, so we are continuing it. And the only thing here is that we have two equations in 2D solid mechanics. So either they can be plane stress or plane strain. So these are the most popular cases, in which case we have two displacements u and v, and then we have three stresses sigma x, tau x, y, and sigma y. And then so the governing equations are given in terms of stresses. And the stresses have to be related to the displacements through strains. So this is three strain components. So all these things which we discussed, so I'm just trying to recapitulate quickly. And then we have this one, and the stresses and strains constitutive equations depends on the material. And so obviously the D has the same 3/3, but however, it will be different from plane stress to plane strain. So coming back to this weighted residual formulation, this also we have done yesterday, is that so we take one equation at a time and then multiply with the weighting function here, right? And then the weighting function here, again another weighting function here to take care of the boundary condition on the traction boundary condition, right? So this is the traction boundary condition. And so similarly second one, so we have another weighting function, and then we also have another weighting function here for the traction boundary condition, where they are Tx and Ty are the two components of T here. So this is the T here. Okay, so which is prescribed. And going through the same procedure. So I just did not write two steps here. One is that this integrating by parts. So then you will have a term here like wi comma 1 sigma x nx wi comma 1 tau xy and y, and that gets cancelled, right, with the term here, and then leaving only Tx and Ty here. So this we have seen in the case of heat conduction, and also I showed it yesterday to some extent. And so quickly in the matrix form, so this is the two rows of weighting functions and multiplying sigma x, sigma y, tau x. So this is exactly the same thing as this. So the top row corresponds to this first equation, and the second row corresponds to the second equation. Okay, and so that we can write down the equations quickly and systematically. So then we have the strains in terms of the derivatives of the displacements, dou u by dou x and epsilon y dou v by dou y, and this is dou u by dou y plus dou v by dou x, and then this is the one which we identify as an operator. So simply a 3/2 operator. So it has meaning only when you operate it on the displacements uv. So similarly, a similar manipulation of this one. So this is the first row, this is the second row. Actually, if you work it out, you can see that this similarly exactly the same L operating on these weighting functions wi comma 1 and 0 wi comma 2, and then we take a transpose. This is actually 3 by 2, 2 by 2. So this is 3 by 2. So you transpose it. So exactly you'll get a 2 by 3 like this one. So which can be written as L operating on the weighting functions here, matrix, and then the whole thing is taken as a transpose. Okay, so this is how we do it. Let's now go into the approximations. So here also, please also observe here that in this, so I already kept something on the left side here, these weighting functions multiplied by these stresses, and then the other things I took it to the right side. So this will give you in terms of displacements, whereas these are the applied loads, applied forces, whereas the left side depends upon the displacement. So essentially here we have epsilon x, these are all given like this. So let's rewrite these things. I express these strains and the weighting functions in this manner. So let's substitute that in this form. So weighted residual statement. So we will write it as L operating on the whole thing is a transpose, and then there's sigma x, sigma y, tau xy is nothing but d operating on epsilon x, epsilon y, so which is nothing but L operating on uv, right? Okay, so this is what, if you want, you can have this bracket, or you need not have this bracket also. And this is on the integral omega, and then we have so this x bar, y bar are nothing but the body forces. Okay, so this is the weighted statement, a little bit more concise. And then from here onwards, we have to make approximation for UV. So UV here for U and V, which are functions of x, y. So let us choose triangle with 3 nodes. So the triangle with 3 nodes is like this. The whole domain so this is a typical element with ijk as nodes, and then this is a triangle. So where we have discussed this this u, which is written as a plus bx plus cy, is also written as ni phi I and j phi j and k phi k. Right? So this is equivalently written like this. And so the same thing is true for V. Sorry, so just a minute. This is not phi. It's V U I. So similarly for Y V, okay, so this is how we can express the displacements. So U and V, so these are now in terms of the nodal values of the displacements Ui, Vi, Uj, Vj and Uk, Vk, where we know that Ni, you recall that Ni, Nj, Nk are the shape functions corresponding to the node ijk, right? So recall Ni is nothing but Ai plus Pix plus Ciy, and where Ai, you recall, xj, yk, yj, xk divided by twice the area, and yj minus yk twice the area, right? So similarly, Nj and we will have the expressions for Aj, Bj, Cj and Nk. Okay, so this is the shape functions. So shape functions given the location of these A, I, J, K nodes, so we can write down the shape functions and which represent the variation of U and V. So there is also one thing which I want to remind you is that the weighted residual statement here is based on this weak form. Of course, L is a linear derivative operator on UV. So that means that it has first derivatives. So obviously the approximation UV here, if you write it, so this UV should be at least once differentiable within the element, and if it has any discontinuity, it should be only the finite discontinuity at the element boundaries. So this for the element here, so you can write it in the matrix form like this. For the three nodes as a summation in the matrix form. So in the matrix form, this is how it looks like. So the UV at any point, if you want, we'll write it as U at nxy, right? So this is how the variation of UV within the element, and then we also make sure that since these are expressed in terms of N, U is expressed in terms of the nodal values, so obviously the C0 continuity is also guaranteed. So this now satisfies the integration necessity of all the conditions of integration, and this is in the matrix form, it's expressed like this one. You can even write this one if you want. in general, j goes from 1 to 3, or j goes from, in general, ijk, right? So this is the general expression, or sometimes we can also write it in this manner. Okay. So now, having said that, the displacement approximation is now I'm writing it 1, 2, 3, but essentially it is ijk. So j is of course taken as dummy variable, but it goes to ijk nodes. So what is that which we require here? What we require here, the next step is L on U. So we need here, let's evaluate. We need the evaluation of, what is that? L operating on UV, which we say L operating on summation of So here these are at any point u and v, while u and v are now being expressed in terms of the 3 nodal values. So n, this is a summation. So that means that if you expand this one, it will have ith node, jth node and kth node. Okay. So if you want to now operate L on that, and then, so let me just expand it all the same. So L operating on Ni, like this. So yeah, just to make it more elaborate, so that means that for an element you will have all the 3 nodes. So L is what? So you can now, L is now, it's a, if you recall, it's nothing but a 3/2 operator. It's a 3/2 matrix. And so if you expand this one, so for example, L has, so it has dou x 0, 0 dou y, and dou y, and dou x. So if you operate it, so the derivative of Ni with x will be dou x of Ni. So recall it. So the derivative of Ni with x. So if you go back here, if you take the first derivative of Ni with x, so it will be simply Bi. So like that, if you see, then this will become Bi 0. So similarly, this will be, the second row is 0 dou y, and that is nothing but will be Ci. So like this, you have Ci Bi and operating on Ui. So you can very well see that this is the derivatives of this one on n. So similarly, you have exactly the same thing with j, bj 0, 0 cj and cj bj. Okay. So I hope this is clear. So this L, which is operating on this Ni 0, so will be simply, this is a 3/2 matrix operator, and then this is 2 by 2, and operating each of these things on this matrix, so will lead to the derivative of, with x is bi, derivative of y is di. So that's how this turns out to be. And now, okay, fine. So now if you so L operating on uv now will be simply that, and let me just put it as a general thing, pj0 so this is the three terms here, and I wrote it as j here. So that means that j will take values of 1, 2, 3 or ijk. Here, this is a general term, jth term, which will take I, j is equal to I, j is equal to j, and j is equal to k. I hope you can follow that. So I hope there is no confusion calling this as 1, 2, 3. All right. So this is for L is equal to on uv, right? So now, what is that which we have here? The next step is that this is this part. What about this weighting function? What is that weighting function we need to take? So this weighting function, the choice of this weighting function, so they choose, what is the choice for weighting function? It should be same as trial functions or the shape function. So trial function is the same as so what is the shape function here? So corresponding to this, so if you choose the shape function, so that means that you choose ni0. Okay, so if you choose this trial function as ni0, 0 ni, so that's what it is here, corresponding to the ith node. So what is that you will get? So that means that L operating on ni again, right? Just like we have L operating ni, exactly it will be the same. So if you choose weighting functions as the trial functions, you will get two equations. And then if you choose again the trial functions corresponding to jth node, nj0, 0, nj, you will get another two equations. And then if you choose nk0, 0, nk, you will get another two equations. Okay, so like this. So let us just put this as L operating on ni, which so what will you get here? So you will get bi0, bi, right, is exactly same as this one now. So that will be appearing here, right? That will be appearing here. And then, so this is the whole thing, and which should be taken here as a transpose. So now let us substitute everything into that. So substituting everything into that, so what we have is into above equation. So what we get here is that the whole thing you get here, this is now, we'll put it as the transpose of that, this one. So this is corresponding to L on ni, and then you have your d here, So it is D11, 1, 2, 2, 1, 2, 2, D. Usually we write it as 6, 6, could be 3, 3, but since it corresponds to tau xy, it's actually more precisely it should be written as D, 6, 6. And so this multiplying Cj0, Cj, 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 and this, okay. So this is this, and this is the general term. This is this on UV, that is the jth part, right? This is on Uj, right? So actually this is what? Let me also, so this is L operating on UV. So that means that this portion has to be written as a summation. Please make this correction. So this, I have to write it as summation here. So this is this term. So that means that this is over the summation j. So the j goes from over the 3 nodes I, j, k, right? So this this now is equal to, what is that? So here we have weighting function is the same as Ni, and multiplying dx bar y bar or omega of the element. Okay, so this is the equation. So that means that this top one will have 3 terms, okay, corresponding to j1, 2, 3, or j is actually I, j, k. So what we can write here is that simplifying. So we will write everything as kij, and the whole thing is this whole thing writing the whole is so we will replace the whole thing here. So this we will write it as a matrix Kij. So recall what will be this. So this integration is over the area here, right? And then here these are all constants. This B and D and this one C, this Bj is all constants, and then this is nothing but, what is the size of this matrix? So this is 2 by 3, this is 3 by 3, and this is 3 by 2. So essentially totally it is 2 by 2. So this Kij, earlier for one variable problem, Kij used to be one value. Now it turned out to be 2 by 2 because we are dealing with two variables u and v simultaneously. Okay. So this Kij is like this. So Kij is nothing but, as we read, so all these things are constants, and then this integral is only on d omega. So we have it Ej, Ej, and we write this A. So where A is area of the triangle, right? So this is Kij, which is a 2 by 2 matrix, right? So like this, so we have, what is this equation then? So if you choose a summation on this one, so the equation will look like Kii. That means that both J is replaced by I, as well as this is anyway IA. So this is Ui Vi. So sometimes I'm just writing it longhand and sometimes in a summation. So, and this is on this side, and we have so here on this side, on the right side, we have the terms here. Can you tell me what this will be? So if I write it, that F quickly, F by X, F by Y. So quickly, what is that? So this has to be integrated. It is Ni X bar, Ni Y bar, just have another 1 minute. Okay, so this is now integration of Ni. So integration of Ni over the element triangle. So it's nothing but the area divided by 3, just like we did it in the case of, so over the element, so this is nothing but area divided by 3. Okay. So this we have seen in the case of heat conduction problem. So that means that here you have X bar A by 3, Y bar A by 3, and then this is comma Q here, and which depends upon whether the triangle, the ith node falls on comma Q or not. So this, I think this we will just continue in our next thing. So this requires a little bit of discussion. Okay, so I'll just come back. So just for the moment, so we will pause here and we'll continue this in our next lecture. So bye bye.